Well, bring us to the end of the first part of this session. We're moving now for a very short break. Gustavo, if you are there, should we give everyone 7 minutes break? I don't know if Gustavo is there.
Yeah, I'm here. Yeah, we have a break.
7 minutes. Let's have a 7 minutes break, and we are back at 2025 UTC. So that means 7 minutes from now.
Okay, thank you. Eduardo, please put this.
You had your tea. Hope you had your tea, your coffee. You're fully energized and ready for the last 3 talks of the session 4. I have the pleasure to introduce to you Fraser Lewis, who is an old friend and collaborator, a member of Global Hands-on Universe. And Fraser is going to present to us what you can do with a robotic telescope. And believe me, you can do a lot with a robotic telescope, especially in the field of education. So, Fraser, I give you the floor, and I'll let you know 5 minutes when you have 5 minutes left, okay?
Rosie, you just gave away the ending.
Oh, boy. I apologize for that.
That's fine. That's fine. I'm used to it. Yeah. Okay. Welcome. I'm going to probably step up the pace a little bit and talk to you about some of the more kind of advanced stuff, I guess, that you can do with robotic telescopes, but also we'll touch on some of the pretty picture stuff as well. I should say, for those of you that think this is a fantastic talk or can't believe how much rubbish I've actually spoken in 20 minutes, I'll be demonstrating, fingers crossed, weather-wise, I'll be demonstrating one of the telescopes tomorrow, live, around about 2 p.m. or so UT. On Thursday, I'll be telling you about a couple of the European projects that we're working with Rosa and various other partners with as well. And on Friday, if you just don't think that's quite enough Fraser in 1 week, I'll be telling you, we'll be having a look at one of the projects that I'm sort of working on and trying to get you as teachers to try and work your way through them in a kind of a live way in a workshop. So yeah, plenty more opportunities to kind of find out what I'm doing and what I'm all about. I'll be talking today about robotic telescopes. There's a list here of a few reasons why robotic telescopes are useful. I think you probably would have some of these in your mind as well. I guess I draw your attention to the bottom one, which is to stop astronomers flying off to sunny places, which is where all the telescopes are. That's a real shame, but it does kind of help with the carbon footprint. So you know, and again, pluses and minuses with those kinds of things. In telescopes, in telescopes, to a degree, to almost to a rule, the larger the telescope you have, the better. The bigger mirror you put on the back of a telescope, in a sense, the better science you can do. Now, that's not entirely fair. There are some very good science projects with small telescopes, but as a broad rule, larger telescopes sort of gives you more opportunities. There are 3 telescopes in the world that are available to do sort of science and education, and I'll sort of talk about those today. So the yellow dot there represents the Liverpool Telescope. The 2 red dots represent the Faulkes Telescopes, Faulkes, which is the name of the founder of the Faulkes Telescope project, which I work for. And they're based in Hawaii. The telescopes now are in Hawaii and in Australia. That's a picture there on the left of the Liverpool Telescope. As you might imagine, it's not in Liverpool. There are many reasons for that, not least the weather in Liverpool is not particularly good for observing. So the Liverpool Telescope lives on La Palma in the Canary Islands, where it has much clearer sky and a much less light polluted sky. I hope you agree with this statement. If you don't, we can talk later. I know Rosa likes this statement in a way, but she doesn't like it in another way. And we always have this sort of little back and forth. Astronomy generally does not sit directly in the curriculum in many countries. It doesn't sit as a big part. You know, in physics, yes, particularly with the older groups, but with the younger groups, astronomy, it isn't always sitting there. And again, I appreciate there are lots of differences across countries and even within countries. But what we can use astronomy for is to play around with some of the stuff that kids either like or don't really like that much. maths being an example of that, I guess. There's a lot of astronomy maths that we can do where we can introduce some fairly tricky concepts in maths by using astronomy. We've seen this with the pandemic, with all the graphs that we see on the telly, and we hear about exponential growth. Well, what does exponential growth mean? Nobody really knew. Nobody had really heard of the term until 18 months or so ago. We can use a lot of IT. There's a lot of things we can do in Excel, even in things like Python as well. When we start to think about stars and other planets, we can introduce chemistry, biology. And one thing we really, really want to do, I think it's a very good thing for many, many reasons, but the opportunity to get schools and teachers to collaborate internationally is clearly something that I think GHOU is very, very keen to do. An example of that, this is getting a bit old now. This is 9 years old. And I put this thing in, we met up on Skype. Well, you know what? I've done how many Zooms in the last year and a half? Meeting up on Skype is not really that big a deal anymore, but 9 years ago, it was quite a neat thing to do. And schools from these different countries, UK, Ireland, Poland, Portugal, and France, work together to create some data. The image on the left there, hopefully you can see that tracking across your screen. You'll see two little white dots. Apologies for those of you on tablets or mobile phones and so on, but you should see two little dots moving from top right to bottom left of the screen. They are asteroids. One of these was the object they were interested in. The other one is part of that free thing that comes sometimes with science. You observe something, something else happens as well. From that, they were able to create this graph on the right-hand side, lower right of the screen here, which has time on the x-axis and brightness on the y-axis. So time going that way and brightness going that way. And for an astronomer, that's a sine wave. For a mathematician, for a physicist, it looks a bit of a sine wave, but for an astronomer, that's a perfect sine wave. That's an indication that there's some sort of rotation or some sort of orbit going on. Whenever we see a sine wave in astronomy, that's an indication of a pair of stars or of something spinning. In this case, it's spinning. We go back to the talk maybe an hour and a half ago by Jamal, where he mentioned asteroids, and he talked about peanut-shaped asteroids and potato-shaped asteroids and so on. This is an example of what you see when you measure the brightness coming from an asteroid if it's not spherical. So this was a really neat project, and again, a really nice example of collaboration. We've worked with a partner of ours in Germany who's based in southern Germany. He's worked with some other teachers over there, something that we're looking to expand and do more of. And this particular student discovered an asteroid and won first place in a local competition or a regional competition for the science that he did. And these are small, I want to say they're small examples. That's a really bad phrase. These are small scale interactions, one student here, one student there. For the students, I think it's a big deal, but we sometimes struggle to get lots and lots of students through the process. So the two are sort of a balance. You either do lots of things or you do some things very, very well. And it's always a balance that we try and strike. This is another example of one of those light curves. So again, x-axis going across is time, y-axis is brightness. This is the transit of an exoplanet. So this is an exoplanet passing across the face of a star. 30 years ago, 31 years or so ago, there were no such things as exoplanets. We kind of knew they existed. We kind of knew that we would get there with the instrumentation, with the software and with the brains that we had. But 30 years or so ago were the first discoveries of exoplanets. Within 20 years of that, we had a pair of 17-year-old students finding a suitable exoplanet candidate, taking the images, downloading the images, processing them using Salsa J, and we saw an excellent example of a workshop earlier today from John Mora, who was speaking about what you can do with photometry, with data like this, and then using Excel to plot the graph. And again, to an astronomer, this is a perfect exoplanet transit. It's got lots of noisy bumps and wiggles. We can add uncertainties and we can do all sorts of nice maths to look at the trend lines and things like that. So there's lots of fun we can have even from this point onward. I will talk more about this one on Thursday. Sorry, the other one, Friday. This is a project that Rosa and I have been speaking about for a couple of years, let's say a couple of years, just so it doesn't look like we're really lazy. This is thinking about how black holes work, if you like, but this is actually measuring the brightness, the changing brightness of the atmosphere, the environment around a black hole. And again, what you see on the right-hand side is another one of these light curves. And again, don't you know if that's not a sine wave? And if that's a sine wave, there's something orbiting something. And I'll go no further with that because that's where I want to take a group of you on Friday if I can. So I will mention that one a bit more then. From work that we did on some of the black hole systems that we're interested in, pairs of objects where one is a black hole, one is a sort of a normal type star, we were able to get a teacher in Switzerland and one of his students on a paper in the Astrophysical Journal to acknowledge their contribution to the data collection. And also Rosa is on there as well, and somewhere in the middle I'm probably in that paper as well. So again, it's a small success. I want to say it's a small success because it's only one student, but it's a big deal. It's a really, really nice thing to be able to do. Moving on a little bit, we started to realize that there is an opportunity to play around with real data. And this is something you can do with the Robotic Telescope, which is where we came in about 20 minutes or so ago. This is a really nice, I was going to say this is really nice. This is one of my activities. I designed this, so it's not for me to say whether it's nice or not, but we had a lot of fun designing this activity to look at the Hertzsprung-Russell diagram and look at the life cycle of stars and sort of measure the brightness of stars. This is an IBSE type. We call it in inquiry-based science education, or IBL, inquiry-based learning. The Americans tend to use the term modeling for something that's kind of similar, but this is a project, student-led project type activities. I want to say it's quite advanced. It takes quite a little bit of effort, but hopefully the effort is borne out in the results that the students get. But they are playing around with real data and all the bumps and nasty things that real data brings to the table. I'm conscious that I can't remember, where did I start? 25. I've got 10.
You have 4 minutes more to talk, and if you want questions,
so I can talk for 9. Probably,
and then you don't have questions.
That's fine. That's fine. I'll live with that. I was kind of trying to do the maths in my head whilst talk, and that's always a dangerous thing for me to try and do two things at once. Another one of these inquiry-based activities, and again, the web link is at the top there. This is on the National Schools Observatory website, which is another resource I would encourage you to have a look at. This is looking at population studies of exoplanets. So it's kind of looking at real data, but it's not looking at individual data points. It's looking at the population of exoplanets and the parameters, the properties they have, such as their mass, such as their radius, such as the spectral type of the host star. So again, have a look at that if you're interested in exoplanet. There are 20 or so web pages in this activity that give you the background. Now, it's always a danger. How much background do we give the students? How much background do we give the teachers? We can give you loads of background to show how clever we are, or we can give you no background at all and get you to just work it out for yourselves. We try and find that middle ground. So we don't make you work too hard, but we do want to make you work a little bit, because that's where you get the benefit and the enjoyment, we hope. Last year, we were able to secure a little bit more funding and to work with some data that was coming down off the Gaia spacecraft. So this is a European Space Agency mission, which was designed primarily to map the shape and stellar distribution of stars within our galaxy, or of our galaxy as a whole. It has this little headline, 1 billion stars for 1 billion pixels for 1 billion euros. So it's a really, really large camera. 1 billion euros back 10 years ago was a lot of money. There are some really nice educational activities associated with Gaia and with the people we've worked with on the Gaia mission, which again, I would encourage you to have a look at those. Clearly, I'll be sharing my slides afterwards as well, so you can follow up on these. Some of the activities that we designed, some of the resources we designed, and in fact, this one was designed by Sophie, who we saw about 40 minutes or so ago, and she worked on creating background material on what Gaia does. So not just the Gaia spacecraft and what it's looking at, but how Gaia itself works, how it was launched, how it looks after its data, how it looks after its power, and so on. There are some really nice resources within this gaia.ac.uk, including little 1-minute cartoons. So again, for those of you that don't have the capacity to read reams and reams of paperwork on these objects. There are some really nice cartoons there I encourage you to have a look at as well. And from that, we created a little step into the water, a little toe in the water, if you like, of citizen science, of trying to see how far you can take citizens before they struggle. Citizen science, if we think of things like galaxies, zoos, universe, and so on, they are often very small, I want to say repetitive tasks. They're often processing lots of little bits of data. The learning that happens with that is not always clear. So we tried to see if we could put a little bit more learning in there, but we appreciate every time we ask our citizens to make one more step, we probably lose a few citizens. So again, it's this really odd balance that we're doing. This one is based on supernova. It's on a particular flavor of supernova called Type 1a supernovae, which are ones that help us start to understand something about the processes going on in the universe as a whole, such as the expansion of the universe and the age of the universe. Again, I don't have time to go into that. That's an hour lecture in its own right. And Carl is very much the person to speak to about those sorts of things as well, Carl Pennypacker. But this was an activity that we designed to just try and tie in that life cycle of stars, supernova, which are stars that go bang, and the age of the universe. If you have students that don't really buy into that, they're not regular students, because most students will kind of grab hold of some little parts of that. With Gaia as well, we had another example of a student and teacher in East London that we were able to get on a paper. So we were very, very proud of that as well, as you might imagine. Just to mention, Gaia will run till 2025. It finds many, many objects that change in brightness every night. Let's say 10 to 20 objects that are produced on their website. In 2025, we will probably lose Gaia. It will run out of fuel. However, by then, we will have this survey telescope in the southern skies that will be doing a similar type of work, this survey work that the telescopes are doing these days. It's going to produce crazy, crazy, crazy amounts of data, crazy amounts of objects for people to find. And again, this link with the amateur community, with the educational community is fantastic, because there is too much data here for professional astronomers to cope with. So we need that extra sort of grouping of people, and we need to sort of develop things like machine learning to try and do some of this work for us. I wanted to mention the Open University. This is another university that I'm employed by. They run an 8-week free taster course called Astronomy with an online telescope. There's a really convoluted web link at the bottom. But again, if you want to do something that's involved in teaching, and again, they're doing this because they want you to do their degrees, but this course in itself is a little standalone block that they would love you to have a look at, I'm sure. The National Schools Observatory has lots and lots of resources, as does the Fawkes Telescope website, and I'll share the links for all of those. Both projects are not just about telescopes. Both projects are about astronomy, about space flight, about space exploration. So please do take time, if you can, to have a look at those websites. And if you are interested, you can register for those. There's a list here of some activities, just to sort of, again, give you the flavor of the types of activities and how they're set up in terms of the ages and the times that these activities take. If you're in the UK and Ireland, then register following the top link. If you are in Spain, it's complicated, but if you're in Spain, follow the link underneath the Spanish flag. Anywhere else, the easiest thing to do, really, if you're interested in the Fawkes Telescope project, is email me, and I can sort of put you in touch with the right people. The same thing applies, in a sense, to the National Schools Observatory, that you can register as an educator wherever you are in the world, and hopefully get some sort of feel for what goes on there. Rosa, I can see, is probably looking like I need to finish. That's my final slide. So I'm done for today, but happy to take questions. Like I say, any questions you have, please email me, and we'll see what we can do to help. That's it. I'm done.
Thank you very much. This was an enormous amount of information and links. We're all doing that because we have so much to share, which is great. What I suggest is that you share your email in the chat so people can get hold of it and contact you with further questions. But of course, the presentations are going to be made available to you, and Fraser will still present a few more times during this week, so you have more opportunities to join. To join this project. It's an amazing tool to have in schools robotics telescopes are unique and very inspiring, and you should take this opportunity very, very seriously if you can. Okay, we have 1 minute left, but there is no questions, just a few comments, Fraser, that you can please see. And don't forget to share your email, because I'm sure that the team will appreciate this.